Okay, welcome to the continuation of electric drive total 4 tutorial session. So in our last video, we did a very interesting introduction. We talked about DC, really excited, or DC trans motors. Then we started DC series motors, and we said that under it we look at the conventional method, and as you're looking at controlling DC series motors by varying amateur voltage. And we said in this is what you do. So initially, this is what we have, right? RF and RA. This is what we have here. So there's some voltage here. So you put a resistor here. It's called a controller. To cause a voltage drop as a means of reducing the voltage that gets here. And once you've been able to reduce that voltage, you reduce the speed. That's it. Once you've been able to reduce that voltage, you will be able to reduce the speed. So that's it. Okay. We have our question here. Okay, so let's read the question. It says that a DC series motor, we've been given RA and RF, and has magnetization curve at 600 rev per minute to be this. So this is curve at this speed, right? Now, the motor operates on a 230 volt supply. Obtain the speed torque curve for the following connections. Basic normal connection. So basic normal connection means that before we come and connect the external resistance, right? So I'm having something like this here. RF here. I have my RA like this, and I have my voltage source here. So they're giving from the question that voltage source is 230, RA is 0.1, RF is 0.05. So 0.1 ohm, 0.05 ohm, 230 volts. So we're having something like this, right? And they said plot the speed torque. Let me see. Obtain the speed torque curve for the following connections. Obtain the speed torque curve for the following connections. So we've been given IF against E, right? Okay. Now, what we want to do is that we want to obtain speed against torque here, right? Speed against torque. We know that torque is equal to what? Torque is equal to K phi IA. Is K phi IA. E is what? Omega is E over K phi. Omega is E over K phi. So I need to find first IA, right? Let's see. IA. To find my IA, this is a DC series motor, meaning IF is equal to what? IA. So let me take the first 2 points. The first 2 points here are 25, 50, 57, 106. 25, 50, 57, 106. So my IA will be equal to IF. So IA2 will be equal to 25, 50. IA will just pick the IF values. IA will just pick the IF values. Okay. Okay. Now we have that. Now let's move on. Now I have my IA. What else do I need again? I need to find the back EMF of the motor here. I need to find the back EMF of the motor here, right? So I know that E of the motor is equal to V minus IA RA. It's equal to V minus IA RA. So I'll take my V 230. 230 minus IA 0.1 times RA. No, hold on, I'm coming. Hold on, I'm coming, okay. I've missed something. Okay. Now, let's find K phi. K phi is what? K phi is equal to E over omega M. K phi is equal to E over omega M. So that's K phi. E over omega M. So by omega, they say the OTC curve was obtained at 600 rev per minute. So by omega M, that is speed in rad per second, is 600 rev per minute times 2 pi over 60. So I'll compute this value here. That will give my omega M. So I'll take each of the E's here. I'll do 57 over the value I'll get here. I'll do 106 over the value I'll get here. I'll put those values here. Okay. Yes, so that's it. Now that I have my K phi, right? Yeah. Now let me see. Let me see the next thing we are supposed to find again. Okay. Now let me find E. E, the back EMF is equal to V minus IARA, right? V minus IARA. So for this first motor here, my V will be 230 minus IA 75 RA 0.1. I'll put the value here. So I'll do 230 minus IA 50 0.1. I'll put the value here. Now why am I finding this E? I'm finding this EM so that I can find my omega. But I know that omega is equal to E over K phi. Right? Not this E, this is a E obtained from a certain characteristic, but then I want the E of the motor as the individual armature current. So then once I have this EM and K phi, omega is E over K phi. I'll find my speed. I'll find my torque as right now I can find my omega as E over K phi. I can find my torque as K phi IA. So I'll put those values here and then I'll plot these two values against each other. I'll plot these two values against each other. So that's what this question is. We're given the magnetization curve at a certain speed, right? Okay, good. Now I'm supposed to find the speed torque for it. So now, let's first find the omega m. We can find it. Just multiply the speed in rev per minute by 2 pi over 60. This is the speed here. Okay. Then now, from our OC curve, we're given IF against E, right? We say we need speed against torque. But when that speed is equal to what? E over K phi. So let me find K phi. K phi is what? K phi is this E here over the omega, the test speed, omega m. That'll give me the K phi. Now that I have my K phi, I also need the back EMF. So that E is equal to what? V minus IARA. So I'll compute that one. Now that I have my E and K phi, I can find speed to be what? EM over K phi. So that's how the order goes. So that's how it goes. So like this here. So you have your IF, K phi, I like this. Now you plot these two values against each other. You plot these two values against each other. Now you realize that when I add an external resistance, so the part B says that, and when you add an external resistance, realize that when I add, I'm cleaning this, okay? When I add an external resistance, the circuit becomes this. It becomes like this. Sorry. You see, yeah, sure. When I add an external resistance like this, right? Okay, sure. Hold on. Okay, so I have my RF here, I have my RA here, and I have my R external here. I have my VA. The only thing that changes in the equation is when I was finding my E. In the first case, when I'm finding my E and I'm doing E is equal to V minus IA, is RA prime. That RA prime is this RA plus RF. So in that case, it was supposed to be what? It was supposed to be in the initial case, it was supposed to be RA plus RF. So that's RA in the question was 0.15. But in the second scenario, when I add resistance, it become 0.15 plus 2. That will be 2.15. The only thing I'm saying is that in the second case, this E equation to become E minus 2.15F, that's the difference. So that's as you can see here. And then you get your E and you plot torque against speed, speed against torque. So that's it here. We realize that when I added a resistance, the speed is supposed to decrease. This is the initial. Initially, this is where the speed is lying here, right? Then adding resistance will cause the voltage at the armature to reduce, hence causing the speed to reduce. So for any point at any torque here, the speed here is greater than the speed here. So that's it. That's the main idea behind this thing. Then yet we say we can also use solid state control. Solid state that involves the electronic circuits. The electronic circuits again. Okay. Now let's look at the same AC, the same DC series motor, the same DC series motor, but how we can control the speed of controlling the speed by varying the field current. By varying the field current. Hold on for me a minute, please. Thank you. By varying the field current. By varying the field current. So let's see how we can do that. Let's see how we can achieve that one conventionally. So by varying field current. Varying the field current. Let's see. So let's draw the same series like this. Right now, here IA is equal to IF. Now, let's see how we can vary the current that goes through the field. Realize that if I connect a resistor here, it will cause current divider. So the current going through here, a portion of it will pass through the side here. If I'm able to vary this resistance here, then I'll be able to vary the current that will go through here. Hence, I can vary the current that will go through this branch here. So that's the whole idea. But he realized that what will change? What will change is that here the IA is not equal to IF. IA is not equal to IF when it's like this, right? IA is not equal to IF. So this one is called a field diverter. So let me call it RD. This is RF. This is RA. The total resistance here is what? Total resistance here RT is this parallel this RF parallel RD plus RA. So where I'm doing E is equal to V, in the table where I have E is equal to V minus IA RA prime, my RA prime, which is the total resistance, will be equal to this here. So that's what to change in the table. This question is very similar to the question we just solved right now. except in the table we said we needed E, we needed IA too, right? Sure. So that's how you find the E. Now also, how do I find my IF? I know that my IF, right? I can use current divider. So IF will be equal to RD over RF plus RD times IA. So I can find my IA. I need IA. So IA will be equal to what? IA will be equal to RF plus RD over RD. That's IA times IF, sorry. So it means I'll multiply all the IFs by RF plus RD over RD. You get it? So RF was 0.05 plus RD. So let's go to the question, we'll see. So, so there's a question like this, right? Where they give us the RD to be 0.1. Example 5. Since 0.1, so just put it here and make your IA the subject here. Also, we said the E2 become this. Where this RA prime is the total resistance. So you parallel them and you add. That'll give you your E here. Once you have your IA and your E, you can just, your torque is equal to K phi IA. Right? You'd have found your K phi from E over omega M already. And then your E is equal to, your EM is equal to what? Your speed is equal to EM over K phi. And you can plot these two values against each other. That's what to change. So say that proceed as in example 8. So that's all. Once you have these two here, it's like the same question, right? Except this place, this place is the total resistance here, and IA is not equal to IF. It's the same table. Once you get this one, you just plot the two. That's all. Okay. Now, you see when we're solving the work, we kept skipping the solid state control, right? I was like, oh, all of them will look at the conventional method. Then we said there's a solid state control that makes use of power electronic circuits to deal with them, right? Okay. So now, okay, so that's the next thing we'll look at. Okay, this video is a continuation to the first, so that's the next thing we'll look at. So I'll end this video here right now, 17 minutes. I'll end it here right now, and then we'll continue in the next video. Thank you very much.